Okay, good morning, everybody. So welcome to the last lecture by Eric on the space of holographic CFT. Okay, so just a couple of announcements. So there will be lecture notes on the website, maybe later this afternoon, which will be updated, in the following days with all the lectures. Questions are welcome, but for that, please speak up such that the fancy microphone can register you. Eric, you should also speak up. That's what you're doing. Students who need a certificate of presence, please sign on the piece of paper that is somewhere here. And if you're online, please log into the live stream with your last name included in the nickname. Otherwise, you cannot get credit for the course. And for people who are from outside, please come to Ricardo at the end of the lecture to get one of these yellow cards with which you can eat without the honey. Okay, so with that.
Thanks. And this being the last lecture, I wanted to especially thank the organizers, so Francesco, Ricardo, and Monica. And so it's the last lecture for me. It's also, Monica's got to get out of here for a while, so I feel a little sad about that, but also it's been a nice honor that she stayed until my lectures were over. So that was the right choice.
I leave right after your
Yeah. To make it worth it. Yeah, thanks a lot. It's been for me a fun few weeks of giving this course, and hopefully also for you. So this lecture is about AdS3 CFT2, the day we've all been waiting for, at least some of us, and AdS3 CFT2 is a topic that could give rise to its own lecture course. And of course, within that, there are subtopics which could be the subject of their own lecture courses. So it's a little bit ambitious to be just giving one lecture about it in a way, so I'll not be able to focus on everything that's interesting about it. And even in the context of this holographic CFT theme, there are lots of different avenues you could talk about. String constructions, you could talk about sort of universal results from the bootstrap, you could talk about relations to pure gravity, ensemble averaging. I'll touch on most of these things at some point today, hopefully, but I also won't assume too much familiarity, so I'll have to introduce some CFT elements first, and we'll see how far we get. I also, want questions as they arise, so please don't hesitate. But maybe one way to motivate what's coming is to return to this question that we talked about briefly at the end of last lecture, which is the scale separation question. So do there exist AdS scale separated vacua? And this bootstrap question, how large can you make the gap to the first state above the vacuum in a unitary CFT with a discrete spectrum? And so in AdS3 CFT2, these questions can be made even sharper in the sense that the theory in the bulk, the theory of 3D gravity, is kind of in this in-between state, which makes it more tractable on the one hand. Gravity is not dynamical in the bulk. The graviton is no local propagating degrees of freedom in the bulk of AdS3, so you can do more explicit computations, but it's still non-trivial because in a space with boundary, there's a lot of dynamics at the boundary, and the theory has non-trivial solutions like black holes. So in addition to this, in AdS3 CFT2, the central charge scales linearly in the Planck mass. But in higher dimensions, the central charge scales for the higher power of the Planck mass. So that means that if from some EFT logic in the bulk, you want to imagine a theory which has a very sparse spectrum, perhaps there are no operators up until the Planck scale, so it's kind of a effective field theory of gravity and nothing else. Then in boundary language, this is a statement that the spectrum of primary operators has a gap all the way until the central charge. So not some smaller power of the central charge, but the central charge itself. And this is an appealing idea to try to test. And so that set of ideas gives rise to the possibility that there is perhaps a theory of pure 3D gravity in AdS3, which is consistent. And by pure, I mean in the sense just described, where you have no states, no perturbative states besides gravitons, all the way up to the Planck scale. And that's where the black hole threshold lives as well. So to start writing something, we can ask, so CFT, then you have delta, the spectrum of primary operators, to order C. This is also a natural thing to ask about in the context of some M-theory compactification, where we start with a theory where there's no scale but the Planck scale, and we'd like to ask whether we can put M-theory on a very small internal manifold and give rise to an AdS3 solution, where there's just nothing up until the Planck scale. So AdS3 seems like a setting where this might actually be possible. So it's a natural question in AdS3, and just to write a few of the reasons why this setting is special. AdS3 gravity contains CFT holes. In contrast, AdS gravity in higher dimensions need not contain the higher dimensional analog, namely AdS Schwarzschild black hole. Of course, Einstein gravity does, but if you look at a more complicated theory in the bulk, say some bona fide string theory or some higher spin theory, AdS Schwarzschild ceases to be a solution. But in 3 dimensions, there's a universality to the space of solutions, and every theory of AdS3 gravity includes BTZ black holes. AdS3 gravity is also renormalizable, and this is essentially the same statement that it's at the classical or semi-classical level can be recast as a topological stage, maybe, albeit for a non-compact group on an unusual space.
I didn't understand your comments about need not contain IDs, because the examples that you gave, I mean, they don't have standard gauge invariants, right? So if I have this invariant, the diff invariant theory in the bulk, don't I generally have?
Well, the examples I gave have diff invariants, but they might have extra gauge symmetries as well. I mean, string theory at finite alpha prime doesn't. In the tensionless limit, it does. That's the higher spin realm. But just even, at finite alpha prime, the solution either gets corrected or gets replaced by something more complicated. I mean, at finite alpha prime, it gets replaced.
Being corrected, but
so there are black holes, but they're just not vanilla AdS Schwarzschild black holes.
they're not exactly.
Yes.
Whereas you're saying BTC is always a solution regardless of what you might have.
Yep. Yeah. And so then, there's sort of a third equivalent statement here, the normalizability, sort of a statement about the topological nature of the bulk. And you can also say that it's just theory of gravitons, that is, the graviton only has degrees of freedom which live at the boundary. In a sense, we'll articulate a little bit more later. The other special thing, here maybe, which is the following: 3 gravity cannot shuffle linearly to matter. So we talked about this briefly in an earlier lecture. What do I mean? I mean that here, the stress tensor dynamics form a closed subsector of the theory on the boundary. So in boundary language, we look at a 3-point function like this. This is 0. O not made with stress tensors. So if you have some matter, which is some non-stress tensor composite operator, then this is 0. That's the statement that the stress tensor forms an algebra, the Virasoro algebra, in 2 dimensions, which depends only on the central charge and is not sensitive to the rest of the content of the theory in the sense of 3-point coupling. In higher dimensions, on the other hand, these are non-zero, and that's the statement that the stress tensor dynamics are non-universal. Okay. All right, so let me now spend a little time introducing some of the elements that we'll need on the CFT side. I'll try to find the right balance of assuming and not assuming some background here. So we have our stress tensor. We have our usual cross ratios. We have our usual coordinates on the plane, z and z bar, so they're complex coordinates on R2. Okay, so tracelessness tells me the off-diagonal components of the stress tensor are 0. And then the diagonal components we call T of z and T bar of z bar. It splits into holomorphic and anti-holomorphic sides. Okay, so we can develop a mode expansion. So V sum for n values and integers of the modes Ln over z to the n plus 2. And the Ln form Virasoro algebra, which I will write here. Okay. There's the central charge. Good. Now, in the language of higher dimensional CFT, that is just talking about global conformal symmetry, the composites of the stress tensor, so say T to the n, so I take an n-fold composite of the holomorphic stress tensor, has 0 twist, right? So let us introduce some notions of modules. Just some basics here. If we have some Virasoro primaries O, then we can form state by acting at the origin with this local operator. And the primary condition is that Ln for a positive mode number annihilates this. L0 gives me a dimension of O, then the right moving dimension H, left moving dimension H, right moving dimensions H bar, H plus H bar gives me delta. And then we generate the rest of the module by acting with the negative modes. So this is a lowest weight state. And so all of the L minus n's acting on this will generate the rest of the Virasoro module. Okay, a Verma module, if there are null states, things can get a little hairy, but in general, you just act with any L minus n, and you're going to generate some state in the Virasoro module for this operator. Oh, okay. So L minus 1 acts like derivative, right? It acts like translation, and so on. The L minus 2, right? So one special case is that the stress tensor itself is L minus 2 acting on the vacuum. The vacuum is annihilated by L plus or minus 1 and L naught. That's this SL2R invariance of the vacuum. So L minus 1 annihilates the vacuum. For a non-vacuum state, L minus 1 is not annihilated. Just gives you the level 1. Okay. So it's useful to keep in mind, as I was saying, thinking in terms of d-dimensional CFT language, right? In d dimensions, there's not a Virasoro algebra. We just have the global conformal algebra. But you can always take your Virasoro module and decompose it into global modules. There's an infinite number of them. And so for every Virasoro primary O, this is a Virasoro primary O that obeys these conditions. There's an infinite set of global primaries, O, then a composite of T with O, then a composite of T squared with O, and so on. All the way up to infinity, you have an infinite number of these just obtained by taking composites of the stress tensor itself with O. And this is somewhat schematic, but it serves for the current discussion. Likewise,
the global primaries.
Sorry?
It's obvious that global primaries.
Yes. So yeah, because the global subgroup of Virasoro is SL2. So when you act outside of SL2, you're going to a new global module, and right, L minus 2 is the mode for the stress tensor. So the action of L minus 2 increases the charge and changes the quantum number such that now you have a new global primary.
Yes, sir.
In other words, this cannot be obtained from this by acting with the SL2 mode.
Okay.
But you need corrections in general to make it really a primary.
Yep.
Like del squared.
Yes. So, for example, right. So this also applies to the vacuum itself, right? So take O to be the identity. That's a global primary. Then you have T, the global primary. So right, T is not a Virasoro primary. That's clear. It's a global primary though. And then you have like a T squared, but the T squared operator has some sort of subtraction. So if we take O to be the identity, then at level 4, you have this operator, sometimes denoted lambda 4, which is like 3t z minus 3/10 d squared. So this is global primary, but TT is not. You need the subtraction.
And del squared, how do I see it? Del squared, I see the L minus 1 or?
Yeah, so this is in modes. This is the same thing as L minus 3 squared minus 3, there might be a 2, L minus 4. But d squared is like L minus 1, L minus 1,
Oh, okay.
minus 2. Use commutation relations, and those just increase the L minus 2 to an L minus 4.
Okay.
Yeah. Right, so because once you move the L minus 1s to this side, they're acting on the identity, and L minus 1 annihilates the identity. Yeah. Okay. Good. So if you're computing a 4-point function, for example, of Virasoro primaries, then you can expand it in Virasoro conformal blocks, which, just like the same way that global conformal blocks capture the contribution of a full conformal multiplet to the intermediate channel, the Virasoro block captures the full contribution of a Virasoro module to the intermediate channel. And the Virasoro block itself can be decomposed into an infinite sum of global blocks by the same logic as applies for the construction of the modules themselves. And that's often useful. Notice that an infinite central charge states that have a t in them, where the stress tensor 2-point function goes like C. Those states will decouple from the exchange of a 4-point function. So you have some exchange here, and you have E O exchange between some external operators. Then the norm, so when you compute the exchange of the state, you divide by the norm of the state. The norm has a C in it because it has a T in it. So if you take C to infinity, that contribution will go to 0. The only thing that is left is the original Virasoro primary itself, and the Virasoro block turns over to the global block. Because all the Virasoro descendants have C's, and those drop out because the norms diverge, and so you are essentially removing the stress tensor from the spectrum because the norm, once you renormalize things by C, then it goes to.
You're assuming that the external states don't scale.
Yeah. Okay, so that's just a small comment on passing. Good. So we can define a character. So right, every operator, you might sometimes see this kind of notation, O, H, H bar, right? And unitarity is the statement that these are non-negative. You can sometimes form canonical variables, dimension, and spin of the name J by taking the sum or the difference of these things. Okay, great. So we can define a character. I H, H bar, which is a trace over the Virasoro module labeled by H and H bar of Q to the L naught minus C over 24, Q bar to the L naught bar minus C over 24. So we have this theory on the cylinder. To compute this trace we identify, that gives us a torus. So this Q is e to the 2 pi I tau, where tau is the tau of the torus. And we're taking the trace over the module of the state OH, H bar. And so this is just a counting function for the states in the module. How do you construct this? Well, you just act with all the L modes for a non-vacuum module, so there's no special null states. You're just acting with L-1, L-2, etc., any number of times you like. This counting function is up to some overall prefactor, just 1 over the eta function. It's just counting partitions into integers, where here the integers are just the mode numbers of the Virasoro. You can act with to make the multiplet. Is this clear? Okay. So, in other words, we have our primary state. And then you just have a U to the theta. You have 1 on both sides, and so that's the formula for character. You might ask, can you have C left and C right? That is C and C bar be unequal. You can. I've just chosen them to be equal for simplicity, but there are interesting things to say about theories where the Virasoros on left and right have different central charges. We'll briefly come back to this in a little while. But the difference between them is constrained. Why is it constrained? Well, the theory must be modular invariant on the torus, which is the subject we're going to turn to now. Any questions?
You're saying the CNC bar could be different?
Yes, CNC bar can be different. But the invariant under the T modular transformation requires that C left minus C right, or C minus C bar, must be a multiple of 24. Why is that? Well, as I take tau to tau plus 1, this will pick up a minus C over 24. This will pick up a minus C bar over 24. And so C minus C bar being a multiple of 24 will just turn the phase into a 1, so that term by term it's invariant. Of course, you also get an H minus H bar, but again, T invariance requires that the spins are integer quantized, as you'd expect in any dimensional physical theory. When C minus C bar is non-zero, the theory is said to have a gravitational anomaly. There's interesting physics about that, and also in the context of holography, that gets into this realm of topologically massive gravity. You can ask some other questions about that. But I don't want to say any more about that. Okay. So we can just count the states in the theory by constructing the partition function. And right, so in 2 dimensions, the partition function. So we put the theory on S1 cross SD minus 1 in D dimensions. That's the space relevant for radial quantization and for counting local operators. When D is 2, that's S1 cross S1, which is a torus. So the partition function we're interested in is that for the theory on the torus with a modular parameter tau. And I'm writing Z of tau. It depends non-holomorphically, though, on tau, but this is just a simple notation. Okay. All right. So in general, what form does this take? Well, we assume, for the sake of this course, that there is a identity operator. There's a normalizable ground state. And so the vacuum gets counted, right? So the partition function is just this trace, where you trace not just over a single module, but over everything. Okay. So expanding in characters allows us to identify the Virasoro primaries, and then Virasoro symmetry does the rest of the work for us. This is just a Virasoro primary counting function, at least once you strip off some factor of eta here. But in general, we can write this like so. Okay, where again, I tau is 2 to the H minus 1 over 4 Q squared. And the vacuum character is not exactly chi 0, 0. There's an extra null state because it preserves the full SL2R. And that means in particular that L minus 1 annihilates the vacuum. It doesn't annihilate non-identity operators. So there's an extra null state here. Right, chi vac as chi 0, 0 times 1 minus Q 1 minus Q bar. So this removes the L minus 1 from the counting function. So these are our characters. That's a partition function. And these are the degeneracies of the Virasoro primary operators. Okay. All right, so what properties must the partition function, must the theory obey? Well, some of them are more of a choice than others, let's say. So there's interesting physics in non-unitary CFTs, but one might be interested in unitary CFTs. And then you will impose unitarity on this object. That's what we'll do. Okay, so there's a unitarity constraint. What does that imply for the degeneracies? Well, they must be non-negative. Okay. They must be non-negative, and the dimensions themselves must also be non-negative. Okay. Now, you might also be interested in CFTs with a discrete spectrum, sometimes compact CFTs in 2 dimensions. That word coming from sort of a history of constructing them by, sort of geometric compactification, where then you have some space which is compact, which generates the spectrum for you. But that term now is just used more generally to mean a CFT with a discrete spectrum. On a compact CFT, the sum is a discrete sum. So I've written it that way to kind of make this manifest. You could, in general, think of this as an integral over some density of states, rho, and then discreteness is the statement that it localizes onto a sum of delta functions. So the spectrum of H and H bar is discrete. So just this, like that, really have a sum over a discrete set of states. Again, each of these can be relaxed if you'd like. Now, in such a CFT, the number of states for a given set of quantum numbers should be an integer because you are counting something. This is what I'll call the integrality constraint. In such a partition function, these are actually integers. And that's, of course, a more refined condition than just unitarity, which requires them to be non-negative. And finally, perhaps this could have been the first one rather than the fourth one. Modular invariance.
Sorry, Eric. Why the generalities may be negative?
Well, they shouldn't be. You're asking why not? Or
why? I mean, physically, you may have a negative degeneracy. I mean, in my mind, the degeneracy is always positive. Or the
well, you can't. In a physical theory, you can't have a negative amount of something. Either you have some states with some dimensions, or you don't have them. In other words, the degeneracies are non-negative. You can certainly write functions where you have negative degeneracies, but then the physical interpretation is just weird and unusual. It's not that of a physical state count.
Okay. It's another.
Eric, there are connections between point 2, 3, and 4, right? Or is something that you impose independently, or because I assume that if you don't have discreteness, modular invariance also is gone, or...
Yes, good question. So I didn't mean to imply that these are independent and necessary and sufficient conditions for a CFT to exist. They are not. We don't know the full set of interrelations between them. First, I should make that clear. But they are not. They are basically independent in the sense that you can have modular invariant functions which are discrete or not discrete. That is, you can have modular invariant functions which can be written as such a discrete sum, or you can have, actually a bit more easily, modular invariant functions for which the spectrum is a continuum, for which you'd write that as an integral over a continuous density of states with support on some continuum of H and H bar. You can have modular invariance without unitarity or with unitarity. You can certainly write down functions which don't obey integrality. That's the hardest one, as you know. But still, there are some kind of redundancies in the spectrum that follow from imposing some of these constraints. So here I have in mind, for example, the statement that if you have a modular invariant partition function, then not all the degeneracies are independent from each other. The simplest version of that is the Carty formula. Other questions? Okay. So we're going to talk about modular invariance now for a bit. So what is the statement? It's this, where gamma tau is just defined to be tau plus b, the fractional linear transformation, tau, A, B, C, D integers, that's D, right, and then this condition, that's the S. Good. So the consequences of this for the spectrum are still being worked out. It's an active area of research. But some of the consequences were known long ago. Carty's formula is the first famous example of the universal consequences of modularity for any CFT with an identity operator, a gap above the ground state. And morally, you can think of modular invariance as a kind of UV-IR relation, if you like. A relation between different parts of the spectrum. The low energy states are small delta states, and the high energy states are large delta states. This can be further refined. There are relations between the states with small h and h bar, in other words, small twist, and states with large twist, large h or h bar. It doesn't have to just be about the diagonal combination. So the Carty formula should be viewed in this light, where you extract the consequences for the spectrum by thinking of the partition function in that language, imposing this and asking what it implies about the degeneracies, for example, or even just the support of h and h bar itself. So for example, if you take tau near the cusp of infinity, then the character expansion, partition function is dominated exponentially by the vacuum state. If we assume there's some discrete gap above that, then all subsequent terms are exponentially small. But morally speaking, modular invariance relates this by the S modular transformation to the tau goes to 0 limit. When the tau goes to 0 limit, Q goes to 1, and then the characters, which this is just some sum over powers of Q, when Q goes to 1, this is the, all the states contribute equally, and so you're sensitive to the high energy tail of the theory. And so in this way, the vacuum determines some properties of the high energy density. That leads to Carty's formula, which I certainly haven't derived here, but I've just tried to convey the spirit of it for lack of time. And so what is the statement? It's that rho large delta, or equivalently d, the degeneracy in that language. So if I look at the degeneracy for a large dimension, so h plus h bar going off to infinity. Sorry for mixing notations a little bit. This goes exponentially. In the dimension and the central charge with a square root. So this is true for any 2D CFT with an identity and a gap above that, some no matter how small, as long as it's some finite gap. And that's an interesting.
Examples with no gap.
So you can approach zero gap in a sort of sequence, like a decompactification limit of, a compact theory, like the free boson. And then this type of property, then this derivation does break down. And instead of getting exponential growth asymptotically, for example, you can get polynomial growth. Yeah, this kind of thing happens in the free boson modular space.
But in a finite box, you cannot get zero gap, right? I mean, in a finite box, just quantum mechanics. So once you put a finite box, you must have a small. You must have a small gap.
Yeah,
Zero gap means energy, it's infinite localization. So just my right.
Yeah, I agree. So if you can think of if there's a box, right? I mean, not every CFT can be thought of as coming from some.
So if there's no box, then the gap is zero. And at least in U95, the gap is 1 over Ry times some N1 N5. So if Ry goes to infinity, the gap goes to zero. But if you have a finite box, it's always.
I just mean that abstractly, when we write down CFT spectra consistent with modular invariance, there's no box, right? It's just there might not be a geometric compactification.
You're putting a torus. You're using modular invariance to put a torus, right? If you don't have a torus.
Yeah, but sorry, but in the free boson case, I'm referring to the S1 of the space. Yeah, it's living.
Yes, that's right. So that's why you need that.
It's a different box, right? Yeah, yeah. So in that context, I agree, but there might not be any way to realize some spectrum geometrically, aka with the box, and then it's less clear what it would mean to exist as a finite box. So then, yeah, that's all.
Normally, I could also imagine taking the central charge to zero, and then I would also get polynomial growth, right? I mean, the fact that there is an exponential growth is that there's some negative Q powers that are driving the.
Yeah.
And those come from the minus C over 24 that you have in the characters, right?
Yes. So let me build on that a little bit. Here is the character for a given primary module, right? This is q to the h minus c minus 1 over 24. C equals 1 is the special point when you talk about Virasoro CFT, because, well, you can see this from multiple points of view. From a representation theory point of view, we know that if c is less than 1, then you're in this minimal model regime where either the theory is non-unitary and may or may not have a finite number of primaries, but for unitary theories, they have a finite number of primaries. There's lots of extra null states flying around. This is the rational regime for Virasoro. Another way to say this is that if you look at the vacuum character and extract the asymptotic density of states just due to the states in this module alone, then this defines sort of a Cardi, let's call this rho vac, dimension. This looks like Cardi, except instead of C, you have what's generally called C currents, where this is the amount of the central charge which is soaked up by the currents in the theory. For the Virasoro case, where there's no extra currents, the currents equals 1. There is one generating element of Virasoro algebra. It's the spin-2 current distress tensor. I'm writing this more generally because you can have theories with lots of extra currents, like W algebras or something, and then this increases. But for Virasoro, this is 1. So the vacuum module looks like it has asymptotic growth with central charge 1. And so if you subtract out the effect of the Virasoro descendants, in other words, if you construct a primary partition function, let's call this ZP now, by stripping off the descendants, so you multiply by eta q squared, and then to keep it modular invariant, you multiply by a square root of tau. So this combination is modular invariant by itself. then this thing is just, so there's a root m tau in front, but it's just the sum over powers of q. And you see that there's the c minus 1. Okay, so what is the statement? C goes to 1. The theory is current dominated. The full central charge is saturated by the Virasoro descendants of the identity. And so this is telling you that there's some threshold in the behavior of the space of Virasoro CFTs at C equals 1. So we might say that for C less than 1, you're in the rational regime. For C greater than 1, we're in the irrational regime. This can be made sharper. I mean, what do these mean? Why is it called rational? Well, the central charge and all the operator dimensions in this realm are constrained to be rational numbers, it turns out. And there's a finite number of primaries in this regime as well. Okay, and here I'm assuming that we're sort of sitting in this sequence of minimal models indexed by some p and p prime. Okay? We can go away from that. It's a bit of a funny regime, but it can be done, but let's not do that. Here, for C greater than 1, there's necessarily an infinite number of Virasoro primaries. Modular invariance requires this. And in general, the dimensions and the central charge are not constrained to be rational. So we call this the irrational regime.
I didn't understand the argument about the center. So you constructed this primary partition function, and then what was happening?
Well, then, so this thing is just a sum over powers of q without the 1 over etas in front. So you're just sort of counting the primaries more directly. Every coefficient is a number of primaries with no pollution from descendants. And then I was piggybacking on Val's comment that C equals 1 is a special value, and you can see it from that formula because, right, when you write this, you stripped off the etas. The eta here puts that 1 there. So you see that the special value is C equals 1, not C equals 0. That was the kind of initial comment I was making, and then I was elaborating on why special things happen at C equals 1. The other way to see that, one other way to see that is to ask about the asymptotic growth of the vacuum module itself and see that it grows with characteristic central charge 1. So somehow the rest of the theory is like shrinking, and the theory is current dominated.
Yes. But this argument about model invariance which you are playing with, it's basically the same which you were talking on one of the first lectures about criticity of B when you have identity greater one channel and output creates another channel. The argument of kind of was universal, it didn't refer to number space-time dimensions. What does it mean in the present context? We agree that the same argument, simply specifying dimensions.
Yeah, and you can even make it even more literally the same by writing the partition function as a certain 4-point function of twist operators, and then modular transformations are crossing transformations. Then it's literally the same argument as like an argument applied to a 4-point function using crossing. But here, yeah, here, so you're asking, I mean, you can phrase the Carty formula in this way.
What does it mean from point of view of double trace operators?
Yeah, it doesn't mean anything about yeah, it's not as specific. It's kind of, there's no microscopic interpretation of what these states have to look like, because all you're assuming to derive it is that there's an identity operator. So the states at large dimension, which must be there, you don't think of them as composites of identity operator or T's. These are primaries. I mean, most of these are primaries. You take C to C minus 1. This is the primary counting. So yeah, there's no such interpretation that's as direct as that in this case. Yeah. But you can make versions of that type of argument in 2D, but they just involve a little bit more. So for example, if you add a primary and then look at its 4-point function and try to play the same kind of game, you do infer a 2D analog of these composite double twist operators. The interesting thing to do then is to ask you have your thorough symmetry, not just global. What does this imply about the quantum numbers of the composites? And they actually do get shifted because of the fact that they kind of get dressed with stress tensor, and then you have to ask, how does this change the dimension of the composite? And there's a formula for this, which is elegant when written in the right variables. I can do your
This one for the anomalous dimension. So a higher dimension, it probably goes like a power of 1 over L. That depends on the dimension. And I guess in 2D is going to be zero.
Great. Yes, exactly.
So what was happening there? And then you might also get some imaginary, right? What is it? Right. So the anomalous dimension, first of all, is not suppressed at large L, which is related to the fact that the gravity is not dynamical in the dual AdS3 spacetime.
Yeah. Mm-hmm.
And then there was some issue, if I remember correctly, when you entered in the black hole threshold.
Yeah. Should I go into this a little bit?
If people are interested.
Yeah. Right. Well, you were following Grisha's questions. So that's at least 2 people. So I'll assume there's.
Well, Grisha, are you interested?
Okay. So.
Grisha is too close to me to say no.
Okay. So the statement in higher dimensions was this. There's an operator O, and we look at its OPE of itself. The identity will appear, and if we organize the rest of the operators by twist, then generically, apart from some possibility of funny light scalars being in the theory, the next lowest twist operator is a stress tensor. Right? Low twist means close to the unitarity bound for the given spin. Okay. So schematically, the OPE looks like this, and this kind of crossing argument, the Lightcomb bootstrap argument, as you pointed out, this implies that there exist these composites an asymptotically large spin. So large spin, there's this generalized free field structure. And this, if you include the first correction, so there's a gap in twist in higher dimensions. Right? This has twist d minus 2. Okay, so this is, so as to avoid some notational clash, let me not write twist as tau. So the dimension minus the spin is d minus 2 for the stress tensor. And this implies that delta and L is the generalized free field value plus some anomalous dimension minus over L to the twist of this, which is d minus 2. As you're pointing out, when d is 2, this is not suppressed anymore. If you take any composite of stress tensors with any number of stress tensors, that also has 0 twist. You're going to get an infinite number of this type of contribution that you would need to resum. You think of it this way, from a dimensional point of view. That resummation amounts to playing the same game, except instead of using global blocks and analyzing the crossing kernel for global blocks, you use Virasoro blocks. So in other words, I say, I have not just the identity operator, but the full Virasoro module of the identity. What does crossing symmetry in a 4-point function of O with that block imply about the composites? And it implies that, right, so in other words, the leading dimension sort of gets corrected because you've resummed all the stress tensor contributions to this 2-particle state in both language. And so now, whereas this in higher dimensions is just 2 delta O plus 2n plus L, in t equals 2, it's that plus some correction, which can be extracted exactly by looking at the crossing kernel for Virasoro blocks, in particular for the vacuum. There's a formula for that which is nice. I won't write it here, but this is in this paper from 2018 I wrote with Scott Collier and Jan Gobet and Henry Maxfield. And I'll just say that if you write the dimensions in terms of Liouville momenta, so if you take h equals alpha times q minus alpha, where c is 1 plus 6q squared, then whereas in higher dimensions, the generalized free field dimension is just the sum of the dimensions of the constituents. The result in 2D is that it's the sum of the Liouville momenta of the constituents, alpha. Hopefully that was helpful. Yeah, that's a good example of how in 2D, the fact that the entire vacuum module is comprised of operators of twist 0 changes the nature of some higher dimensional bootstrap conclusions. But also, sometimes in a computable way, because 2D is nice. Okay. Good. So we'll take a break soon. But this discussion, I think, transitions us nicely into talking a little bit about the different types of 2D CFTs that there are, which will then springboard us to talking about those which might be holographic and what the properties of those would be and how the bootstraps come to bear on that question. Okay. Maybe the simplest type of 2D CFT is a chiral CFT. What does that mean? That means that there's a trivial right-moving sector. So C bar is 0. All the operators have right-moving dimension 0. Everything is just holomorphic on the torus. And so really, this is just dependent holomorphically on tau. More properly, meromorphically. So all operators have dimensions h, 0, and the invariance of the partition function on the torus under T transformations requires that h is an integer, because h minus h bar is spin, which must be an integer, but h bar is 0. Okay. So all the dimensions are integers. The central charge, likewise, must be a multiple of 24. If you insist on full SL2Z invariance, if you want fermions, you can chop that in half. And so it's easy to write down modular invariant partition functions with these properties. It's harder to verify the existence of CFTs with these properties. There's a lot of interesting stuff you can say even just in this realm. These are lacking some of the full dynamics of a CFT with left and right moving sectors both. Okay. A useful way to characterize these theories before I move on is that the partition function is just the vacuum character for some special chiral algebra with lots of currents and lots of null states. Why do I say this? Well, here's the operator spectrum. Everything's a current. But Z is modular invariant. Right? So everything's a current. That means that we can think of all of the operators together as forming an extended chiral algebra that augments Virasoro with all the other currents. And so all there is identity module with respect to this extended algebra. So the partition function is just a vacuum character. For a generic set of currents, this will not be modular invariant. But it turns out that there are special algebras for which this is the case. So you might be familiar with this monster theory at C equals 24, which has 196,883 extra currents at level 2, and then more at higher levels. These have null state relations such that in the end, the J function can be thought of as the vacuum character for the Grease algebra. All right. Now maybe next, simplest, let's say, would be rational CFTs. If the extended chiral algebra is Virasoro, then these have G less than 1, and the operator dimensions and the central charge are rational numbers. There's a finite number of Virasoro primaries with respect to this Virasoro algebra, which itself has special null states. This is the BPZ construction that sort of maybe was one of the original bootstraps. And a lot can be said about this, but we want to think of this as kind of intermediate between a chiral CFT and, let's say, an irrational CFT. Which doesn't have either of these properties. Somewhere in between are things like the N CFTs, free bosons rectified on a lattice. And I say in between because a single free boson has C equals 1. So it's kind of on the threshold of irrationality. And one way you can see this is that there's an infinite number of primaries. That theory, so first of all, that theory has a U1 algebra. So there's extra currents besides Virasoro. And if you ask about the growth of states at large delta with respect to primary with respect to this algebra, it's not exponential a la Cardi, it's polynomial. So there's an infinite number of primaries, unlike a rational CFT, but it's not yet exponential. It's getting there, but it's on the border. In some way, you can think of this as taking the C goes to 1 limit of the sequence of Virasoro minima models, but that limit can be taken in different ways. You can land on different limiting theories. And I don't think any of them is literally the free boson with a free convectification radius to dial, although I'm not, that history of taking C to 1 from below is kind of, I'm not fully versed in it, but it's a little bit subtle, and there's different ways to take the limit. Okay. Now, in the realm of irrational CFT, what's the kind of strongest thing you can imagine, the largest departure from these types of scenarios? Well, you would imagine, say, taking C to infinity or taking C large and asking that there's a large gap in the Virasoro primary operator spectrum. Of course, whether this is possible is a question that one would like to answer constructively. We'll talk about this after the break. Let me just make one last remark before the break and asking further questions, that there's no completely solved example of an irrational CFT. And actually, even that's sort of a bit of an oversell. There's not really close to a completely solved example of an irrational CFT. We don't even have candidate partition functions, which have the properties that we'd want for a bona fide irrational CFT. That is, that they're unitary, modular invariant, of a discrete spectrum, where the spectrum of operator dimensions is not regular in some way. So just as a statement about SL2Z, we'd like to have more partition functions, which could be candidate partition functions for CFTs with these properties, not to mention consistent 3-point functions and so on. So the challenge is great. In Shi Yin's Tazi lecture notes about 2D CFT, I think there's a pretty level accounting of the space of known 2D CFTs. I recommend taking a look at that. And things have changed a little bit since then. These are maybe 5 years old. There's some progress, certainly, toward constraining the space of CFTs. As far as constructing 2D CFTs and trying to solve them in this irrational regime, there's a little bit of progress there. There was a paper by Antonio Antunes and Connor Behan from last year, which built on an earlier paper from something like 30 years ago, and gave some evidence that there might be a Virasoro irrational CFT that can be constructed from a certain type of short or G flow involving minimal models in the UV coupled in a certain way. But I just want to emphasize that the challenge is sort of open. On the other hand, if we think of these as chaotic systems, which has been a more modern point of view on what an irrational CFT is, then it might be too tall an order to ask that you actually can write this down explicitly and solve the thing. So with that philosophy, we'll turn towards bootstrap approaches and back to gravity after the break. But let me just ask any questions and then we can break.
But let's say keys with respect to primary operator is continuous. Which of these three categories is false?
Well, if you want a ground state and then a gap above it, then I don't think you can really think of there being a continuous density starting above a gap above a ground state. So often we want that ground state to be there. And for example, Leakville has no normalizable ground state. It just has a continuum of only scalars also, which is strange, starting at c minus 1 over 24. But there's not, somehow that type of theory lacks a property that we would often like, which is the ground state and a gap above.
I'm a bit confused about your comment because I thought if we take the string theory in AdS3 with a purely NS background which has more than one NS5,
Yeah.
then the dual theory is expected to have a normalizable ground state, but it's somehow supposed to have a continuous spectrum associated to the long strings in the bulk. So I'm a bit confused about it.
Yeah, me too. But sorry, is that there's a ground state and then there's a gap and then a
Yeah,
continuum
so
below the gap?
I mean, the story is a bit confusing, and unfortunately, none of the people who know this here. But so as far as so they want to think about this theory as some sort of non-normalizable perturbation of a Liouville type theory that somehow restores the ground state to being a nice ground state. And so you start with a theory which doesn't have a ground state, and then you do this perturbation, and then you end up with a theory of the ground state. But that theory does have a continuous spectrum of primary operators, if I understood correctly, that are continuous because they depend on the momentum of the strings.
Yeah, I need to understand this better. I have nothing more to say. Yeah, I'm sort of aware of the existence of this proposal, but yeah, I should educate myself.
It's just a statement about the spectrum of strings on AdS3.
Yeah, but somehow what it means to write down a partition function where you have a single state and then some gap and then a continuum. If you want to think of this as a microscopic partition function, say not smeared or averaged, then I kind of don't know what it means in the sense that like in correlation functions, the continuum contribution will be infinitely larger than the one state because in any window of delta, there's a continuum of operators. So I should say no more on this. I personally am confused about it. Yeah, I wonder if I have some comments on the line. All right. Other questions? Yeah.
Image requirement forms would not be
They should be somewhere. They do exist. So it depends what your seed theory is, first of all. So I mean, you could take the symmetric orbifold of a chiral CFT and you get another chiral CFT. You take the symmetric orbifold of rational CFT, then you get another rational CFT. Symmetric orbifolds have an enlarged chiral algebra. That's one universal thing you can say. You take a seed theory, as Virasoro, maybe with some null states, maybe not. Then you take n copies and you mod up by Sn. Then the new theory has a Virasoro to the n mod Sn chiral algebra. It's much bigger than just one Virasoro. In that sense, so whether it's rational with respect to that, I think depends on the seed theory, but at the very least it has some extra currents and it's somewhere here. But
just maybe you wouldn't say that C is less than 1, but still it's rational in some sense.
yeah, I mean, if we just stick to Virasoro, if you take a symmetric orbifold of a rational CFT, that's the kind of thing you're thinking about? Yeah, then you get something I would call rational. Just now with respect to something bigger. Yeah, if you took a symmetric orbifold of an irrational CFT, then I guess I would call this irrational, but it's still sort of morally free in some way because you have lots of extra currents and the spectrum is regular in the sense that given the original spectrum, now the spectrum of the orbifolded theory has some spacings which are inherited from the original spectrum plus the overfold, the tenfold tensor structure. So yeah, normally people talk about orbifolds of rational theories because that's what we actually have in hand. But yeah, you're right. It's where they are on this list depends on what you orbifold it, I guess.
And if you start deforming your orbifolds by exactly marginal operator, if you can do the calculation, let's say a couple of orders in perturbation theory, is that irrational enough for your taste?
I don't know, but I'm not sure about perturbative, but yeah, definitely once you start deforming, then yeah, then it becomes irrational. For any finite value of the exactly marginal coupling, that would be an irrational theory. Yes. I mean, because it depends continuously.
Some of the calculation is finite.
But right. The existence of the exactly marginal operator tells you that there is a moduli space, and all the column numbers depend on that modulus as you move. So most of that space is irrational, right? You can't preserve rationality of a dimension. It depends on the continuous parameter. There might be some special rational points.
Sorry, one last question. Would you agree by saying that all the things that you described right now we more or less know from implementing S invariants of the modular invariance of the particular function? No. Listen to see.
Do you mean everything I've said or everything that we know?
Both.
No, so more, yeah, certainly more is known. Let me answer your question by thinking about things that are not consequences of S or T alone. So the statement of spectral determinacy is something that goes beyond S invariance, right? We're using the full SL2Z invariance to write partition function in a basis. Sorry, it's a little bit telegraphic.
Right. Yes.
Well, we're trying to think of the simplest. So what is the simplest thing we know about 2D CFTs that follows from more than just S or T alone? Well,
The roots of bounds, for example, are mostly known from implementing the S transformation.
Yep.
Cardi formula.
Yeah, but you could have a more precise version of the Cardi formula if you want to know more, not just about the asymptotic growth, and this will rely on the full SL2Z and not just the inversion.
Right. There are also versions of Cardi that apply to the spectrum at large, the spectrum of twists, not dimensions. And this involves taking tau and tau bar to be promoting them to independent complex variables and basically taking an asymmetric limit where you take, for example, tau to I infinity with fixed tau bar and then imposing S, but it's acting asymmetrically tau bar, if you like. That leads to a different conclusion, but it's still morally S. Just so, well, even here, right, these are fully SL2Z invariant. Right, they're constructed out of the J function. It's not something you get just by writing down S invariance. You need the full Klusterman sum to complete that, or Rademacher sum to complete that. Think of it that way. So I don't know. Maybe for the sake of time, I'll just say most of what we know comes from thinking just about S, but definitely not all of it. And there's some important things that come from thinking about SL2Z, especially in the context of gravity, where the SL2Z image of the identity, there's a different black hole saddle point, and all of those are important to ask whether you can have a unitary partition function that includes all these settles. Right.
You want 45?
All right, it's okay.
All right, let's continue. Okay. So, in the the realm of irrational CFT, which is where we're going to stay, we want to understand what the properties of irrational CFTs are allowed to be and how they connect to 3D gravity. And keeping in mind that AdS3 CFT2, when you compute the asymptotic symmetry algebra of 3D gravity, you find the relationship between the central charge and the Newton's constant as follows: 3 LADS over 2g Newton. Before, linear in the Planck mass. Keeping this in mind, the large C limit is a classical limit in bulk. So we want to ask about possible spectra of large C, which then constrains possible spectra of gravity in AdS3. So let me sketch 4 possible spectra and their bulk avatars. So we will draw a spectrum a bit like this. So this is the spectrum of Virasoro primaries that I'm going to be drawing. Okay. We have the vacuum down here. And you can imagine that there's a gap in the spectrum all the way up to dimension C over 12. And I'll use the notation delta star to denote the dimension of the lightest non-vacuum Virasoro primary. Now, where did C over 12 come from? I'll make it a little bit quick here, just in the interest of time. C over 12 is, in bulk language, the dimension of the lightest BTZ black hole. So if you take a BTZ black hole, which in general is characterized by some mass m and spin j, and you look at the massless limit, the lightest such object, you take it seriously as a solution, even though in the massless limit degenerates, then the map between bulk mass and boundary conformal dimension is such that this would correspond to an operator of dimension C over 12. And since every theory of 3D gravity has BTZ black holes, the purest spectrum you could think of, in other words, the sparsest spectrum you could think of, has nothing except gravitons up to here. And gravitons are just Virasoro descendants of the vacuum, so the primary spectrum would look something like this. So this is what you might reasonably call the spectrum of a CFT dual to pure gravity. Nothing but black holes and gravitons. This should be viewed as some asymptotic large C. You can imagine something slightly less aggressive. So maybe you have a gap up to order C. Maybe it's not C over 12. Maybe it's a bit lower than that, but it still scales linearly in C. And since C is more of the Planck mass, you have Planckian degrees of freedom and nothing below that. So this, you might say, almost here. See? And if you're familiar with AdS3 CFT2, you might know that conical defect solutions live in this region. So right here is the black hole threshold. We're talking about states that are below that, but still have dimensions of order C. This means that they are dual to back-reacted solutions in AdS, because the mass is of order the gravitational coupling. And so in AdS3, back-reacted takes on a slightly different meaning, but the sort of canonical set of solutions that people talk about here are these conical defect solutions, which you can think of as back-reacted point particles sitting in AdS. picture here, you imagine starting with empty AdS, then you sort of put some massive particle, and you dial up its mass until it becomes Planckian. It will back react in the sense that there is now a conical defect in the center of the bulk that any observer, no matter how close they are to the asymptotic conformal boundary, can detect. So if you sort of go around the angular direction, you can tell that there is a defect angle generated by this massive object in the center of the spacetime. Okay. So there's, of course, something even less sparse. So you could have some set of dimensions where if this up here is the black hole threshold, then we have a bunch of light operators too. Okay, so these would be order 1. And maybe this is scale separated. Maybe you have a sprinkling of these, and then there's some power which is pushed up high, not to order C, but a string or something. And maybe it's not scale separated. You just have some KK tower. I'm not trying to make that distinction here. So we could think of this as, K in the cases we're familiar with, or maybe scale separated to the string scale. But these don't have a Planckian gap in the spectrum. And this one's in red because this is the kind of target that we'd like to shoot for from the CFT point of view. We can phrase this, so these labels are just motivational from a holographic perspective, but we can phrase this as a sharp CFT question. What is the largest possible gap as a function of central charge?
Yeah, sorry, small question. Do you know the corrections to the C over 12? I mean, like, is it C minus 1 over 12 plus something?
Yeah, that's the kind of natural suggestion from the bulk, but even that is a little bit shaky. So, as I said, the dual solution is actually a massless BTZ black hole. What that means, so the horizon size, the horizon radius, is written R plus. The BTZ black holes that are spinning can have outer and inner horizons. R plus is the notation for the outer horizon. It's a radial coordinate R. This is controlled by the mass. When the mass goes to 0, this goes to 0. Strictly speaking, this is not a non-singular classical solution anymore. But to talk about one-loop corrections to the energy around something which is not a proper classical solution is a little bit iffy. Nevertheless, yes, the natural suggestion is C minus 1 over 12. Something you can derive in more restricted settings where the bulk is not Einstein gravity, but chiral gravity. However, I'd say that we don't know in gravity what the quantum corrected black hole threshold should be.
Can I just start adding some higher derivative terms and try to resolve this massless limit, or?
Yes, you can do that, just like in these higher dimensional
Small black holes.
Cloaks, yeah. The question is, if you don't want to add a kind of extra structure, is there some kind of universality to the threshold? Yeah, but that can be done and has been done. Okay, so all this discussion is meant to motivate the CFT question. What is this bound on the spectrum as a function of C? Going back to the first lecture, this was the very first kind of canonical bootstrap question. Okay, how high can we make the gap in the spectrum? In 2D, you can phrase this as a question about the gap as a function of central charge, where you have this extra VSRO structure. And so in 2009, again, a year after the Bertazzi, Richoff, Tony, and Vicky 4-point bootstrap paper, Simeon Hellerman wrote a paper introducing this idea of the modular bootstrap. So what is this? It's the idea that if you treat your partition function abstractly, you leave the degeneracies as free variables, and you insist that it's modular invariant and has a vacuum state and a gap above it. Imposing SL2Z is a way of constraining those degeneracies, and this can actually be done meaningfully with interesting results. And it's exactly analogous to, and can literally, in fact, be mapped to, imposing crossing symmetry on a 4-point function. So you think of your partition function as a function of degeneracies D. You impose SL2Z invariance, and you ask how are the degeneracies and the sum of operators itself constrained. Okay. Sorry?
Did you say that this can be mapped to like a crossing symmetry of 4-point function?
Yeah.
Could you expand on that?
Sure.
Because here we have the CFT data, OP coefficients as well, right, into the problem. And the partition function, those would appear.
Yeah, so it's the partition function can be thought of as a 4-point function of a twist operator with specific dimension, which is linear in C. And the OPE expansion of this 4-point function is maps to the Q expansion of the partition function. So the OPE coefficients are the degeneracies, morally speaking. So crossing of that is modular invariance of this. In particular, Z goes to 1 minus Z crossing is the S transformation in tau. There's a map between tau and Z. So I think Z is the so-called modular lambda function, and so Z goes to 1 minus Z is a S transformation of tau, which you can infer from this kind of definition, and then likewise for other SL2Z elements and other crossing.
Very special 4-point function.
Yeah. So it's for this. It's not for an operator in the theory per se. You take your abstract theory, whose partition function you want to study, you double it, and then you sort of glue together the two copies across a cut, which is at the endpoints live these twist operators, right? So the branch cut between the two twist operators on each copy. It's a 4-point function of twist operators. And these two things can be glued into a torus. So it's manifestly mapping the torus partition function to this twist operator 4-point function. But the twist operator is, encoding the data of the original theory in some implicit way. It's not some operator in the spectrum of the CFT that you're originally considering. Yeah. Okay. Let me sketch how this works. And part of Simeon Hallerman's paper's success was that so back then, solving crossing or doing bootstrap was relatively unsophisticated compared to now. The algorithms were not, there was no semi-definite programming, the numerics were much more rudimentary. The light cone bootstrap had yet to be discovered. So Simeon just kind of picked the S transformation of SL2Z and imposed it by hand on a very special slice of the partition function where you take tau to be purely imaginary, and you impose S in an expansion around the crossing symmetric point, tau equals I. And it turns out that you get non-trivial results from this. So a priori, not clear what this buys you, but it turns out even in his original paper using just like simple algebraic manipulations, you get some nice bounds. And they've been improved over time, but not all that much. The methods have been improved, but the results haven't changed very much. Okay. So we have good. We have our partition. Remember, everything depends on homomorphically on tau here. So in accordance with Jonas' question, you can focus on the S transformation. Tau goes to -1 over tau. And you impose on this object that v of tau equals v of -1 over tau. So there's a few simplifications that one can do to get started. First, this. Second, you take what's been called the spinless limit, or do the spinless bootstrap, where we have our complex tau. We take tau bar to be minus tau. Okay. And so if you look at a particular power of q and q bar in this sum, the h, q bar to the h bar, well, q and q bar become related when you do this. And this is just e to the 2 pi tau delta, where delta is h plus h bar. Right. So now you're just sensitive to the deltas and not the j's. There's yet another simplification you can do. Now, we take tau to be purely imaginary. So we've kind of done the simplest things we can do. Now we're done simplifying. In this case, now this typical term turns into e to the minus 2 pi beta. Okay? And we're summing over a bunch of deltas with some unknown degeneracies. Now we impose modular invariant. So in this set of simplifications, v beta equals e to the pi c of this x times beta. That's the vacuum. Times the sum over delta v of delta e to the minus 2 pi beta delta. And here I've tossed out this information of the characters, but you know, we find this by looking at the primary partition function. In Simeon's paper, he started out this way, and that helps you a little bit. Now, we impose S invariance. And so we can define in capital phi back now. That's the difference between the two channels. Or in the end, we're taking tau to be I beta. So this is just inversion of beta. And likewise, the non-vacuum characters here. Okay. And so S invariance is just a statement that phi back of tau. And let me write beta here. Use the mix up. Plus the sum of the dimensions, which are positive, times the degeneracies d of delta by delta beta equals 0. So let's do modular bootstrap in two versions. The first is the simple original version. And around tau equals I. Equivalently, beta equals 2 pi. Here where tau equals I beta. Yep. So you can expand this equation around this crossing symmetric point, right? I goes to -1 over I is I, so it's S invariant. You expand this around that point. You get derivatives, and order by order, you impose this equation.
So you mean beta equals 1, right?
Yeah. Yep. Yeah. In this convention, yes. Sorry. Yep. Yeah, it's always annoying. Thank you. Okay. Now, these days, we can do better by employing a functional approach, exactly like people do for the 4-point function bootstrap. Where you find some functional omega, which obeys two properties. The first is that omega acting on by vac is positive. And the second is that omega on phi delta is non-negative for all delta above some delta star. Okay. Suppose you can do this. You're acting on this equation with this functional omega. If you can do this, and this piece is positive, and if this is positive for all delta above some delta star, then there must be an operator with delta less than delta star, else the equation can't be satisfied.
So this function basically depends on the vacuum and this delta star, right? Can we say this?
No, it doesn't depend on them. It is some. You're acting on some things which have a delta dependence, but the functional itself is not. There's no delta.
To satisfy the positivity properties, that is contingent to the fact that we have a delta star above which this omega is positive. Okay, so we can say
Those conditions.
exactly. That's why I'm saying it depends on delta star in a sense. And the
You're looking for a delta star for which you can find such a functional, and that's your bootstrap out.
Right. Okay.
This is unfortunate. All right. Now we get to say what the result is of doing this. And this has evolved over the years. It has involved analytics and numerics. So what's the result? Okay. Let me now switch orientation. Okay. So here's 0. And I'm going to quote the asymptotics of the result at large C. We'll return to that in a second. So Simeon's result was C over 6. So it's linear in C. Right? This is a first principles fact about 2D CFTs that was not known before. It's intrinsically interesting. It's linear in C. The coefficient is 1/6, and if we recall from gravity point of view, we wanted to achieve C over 12. Said a little bit more, giving holography a bit more credit, we think that we should be able to push it down to C over 12 because we should not be able to have a theory which is dual to something in the bulk without BTZ black holes starting at C over 12. That's the prevailing philosophy behind this field. But in Simeon's paper, he found C over 6. Now, C over 6 is also special in holographic context in that that's the sort of dimension above which there's a certain universality of the Carty density of states, but that's not really the argument that seems to be relevant for where delta star should be. Anyway, that's a side point. We can return to that. So that was 2009. Then there were several papers, all of which I quoted in the reference list that I think you received. And so let me now quote the best analytic and best numeric bound. Okay.
Analytic or
Yeah. So this is, of course, not the scale I'm about to draw. We're large C. Okay. Now here we're at C over approximately 8.5. This result is due to Hartman, Mazach, and Rastelli from just 3 years ago or so. And the best bound overall comes from numerics. Down here, C over 9.1 or so. And where we want to get is here. So this is the best one so far. And
Sorry, so all these just use modular invariance of the torus partition function, right?
yes,
We don't look at the torus 1-point function, for example.
correct, because that's right.
And this best numerical bound, is it just for the S transformation, or can I just play this game for tau minus gamma tau? And
Yeah, good question. So right, so you have these three simplifications. Yeah, so the numerical bound came, the analytic bound came from sort of a different perspective. It's easier to talk about this. And this one imposed the spinless condition and generalized the other two. So I think they did just use S, in fact, but they were exploring a wider neighborhood of tau, but with the spinless condition imposed.
is there intrinsic? I mean, the equation is the same if I change capital phi to be the difference between the character at tau and the character at gamma tau,
Yep.
right? And then I have four
Yes.
or three integers that I can play with my functional, and like, is it just a technical difficulty, or like conceptually there's something hard in doing this functional method to?
No, it's more, well, it's a little of both. So
Can I make a comment?
go ahead. Sure.
So the tau to minus 1 over tau in some clever variables, it's just a Fourier transform of the characters that Eric was writing down. And it looks like having to deal with Fourier transforms and eigenfunctions of the Fourier transform is easier in that setting. Now, if you have a general gamma tau, then there's a general transformation, and I don't know if there is a nice piece of functions transform nicely, and that's the short version.
That's true. Yes. So one reason that S is special. So there have been some attempts to try to explore other regions of the fundamental domain. And for example, if you look at the ST cubed invariant fixed point instead, then right, you specialize tau to this corner value, and then the Q expansion involves phases. Here, there's no phases, so it's a positivity question. In other words, you want to work with tau in such a way that you're preserving positivity as much as you can. And for example, trying to do some perturbation theories of, around this ST cubed invariant fixed point, you have this -1 over j, and now you're getting in trouble. And any other generic point will have some phase. So that's part of the issue. And similarly here, right? As you get spin, then you get away from this manifestly positive expansion, right? Where if d were positive, then the expansion would be manifestly.
So the strong form of the holographic argument is that I need to take into account the spin and I need to like do everything to get to C over 12, right? Or,
Yeah, that's yes. And on the modular bootstrap side, that has not been implemented. So yeah. There are arguments that if you use modularity alone, but full modularity, then you won't be able to push this below C over 12. This is a little different question. I mean, you'd ask, okay, we'd like to push it down to C over 12, and you might ask, can you push it further? Maybe the gap's actually not all the way up there. That's certainly possible. But if you just use modularity alone and don't impose, for example, discreteness or integrality or something more refined, then there's a limit on how well you can even do. But first, we'd like to do that well, and then yeah. So this leaves us slightly short of showing that, suitably understood, every 2D CFT is dual to some bulk theory, which has black holes. And still, though, you can ask about whether such pure theories of gravity exist and try to actually just construct a partition function which has the flavor that you want for such a putative theory. So there's an ongoing quest which started, let's say, in 2007 with a paper by Witten, which revived the question of whether such theories might actually exist by emphasizing some of the points that I emphasized earlier about perturbative renormalizability and the existence of PTZ black holes and so on. I definitely won't be able to cover this quest in the next 10 minutes. This would be a good subject for its own lecture. Let me just sort of give a broad overview of the history and where it's led us. In the references, there's a chronological history of this. Okay. So what did Witten's paper do? Well, he said, yeah, these theories might actually exist, and he introduced the notion of an extremal CFT, a terminology which was then later co-opted by bootstrap practitioners to mean a CFT which saturates some consistency conditions. In Witten's case, he had something more specific in mind. He was imagining that the dual theory to pure gravity was actually holomorphically factorized, a product of a chiral CFT on the left and an anti-chiral CFT on the right. And in this more limited setting, he wanted to construct the partition functions that had the maximal possible gap consistent with modularity. In chiral CFT, because the partition function is meromorphic, there's a lot of power that comes from that, and you can sort of write down the candidate partition functions rather easily as polynomials of the modular J function. And so he wrote down these putative extremal CFT partition functions and got people thinking about whether this could actually be dual to a theory of gravity with nothing else. After all, he wrote down partition functions which seemed to have something close to the right gap, although has this chiral factorization property, which was really not so well motivated from the gravity point of view, as he was quick to admit himself. Then, a year later, Maloney and Witten wrote a paper which was inspired by Witten's paper and also by the black hole fairy tale paper from around 2000 or so, to try to actually do the bulk path integral as a sum over smooth solutions. So this paper from 2000, the black hole fairy tale, by Dijkgraaf, Maldacena, Moore, and Verlinde, was studying the elliptic genus of the D1D5 CFT and showing that it could be written as a Poincare sum over SL2Z images of some seed object, which had an actual gravitational interpretation as the saddle point partition function of the vacuum, dressed appropriately with S3KK modes and the like. And they interpreted the SL2Z sum as a sum over bulk classical solutions dressed by perturbative excitations. This looks like a semi-classical approximation to a path integral in a situation where you have a bunch of saddle points. And so what Maloney and Witten said was, let's now consider non-supersymmetric gravity in AdS3, not an elliptic genus. We compute the partition function. And we want to imagine that the path integral, the partition function, can be computed as a sum over smooth saddle points, that is, solutions to the classical equations of motion of Einstein gravity. Just with graviton excitations around each saddle. Now, what are the saddles? Well, in Einstein gravity, the saddles are just pure AdS3. If we're on the torus, this is what we'd call thermal AdS. And then all the BTZ black holes. And in fact, starting from the pure AdS3 vacuum, if you want to get to the BTZ black hole saddles, all you have to do is perform an SL2Z transformation. So if we start from empty AdS with both cycles identified, right, then there's a time cycle and a spatial cycle, which I'll call phi. So if this is the Euclidean time, just call this t, and this is phi, this is the boundary torus, and the bulk fills this in. So you want to think of this as a solid torus. The interior is filling in the boundary torus all the way until you get to the center of the spacetime, the would-be Poincare horizon and Poincare coordinates, where the spacetime just ends smoothly. Here, the spatial cycle is contractible, but if you switch space and time, then the time cycle is contractible. And as we know, this is the Euclidean continuation of a black hole geometry that we use to compute partition functions and establish thermodynamic equilibrium of a solution. So to go from here to here is like going from this solid torus, where you have this labeling of space and time, to some SL2Z image of this solid torus, which in the simplest case, say if I do the S transformation, this just swaps the spatial and time cycles. And now time is contractible, and this is a BTZ black hole in Euclidean signature. There's a whole so-called SL2Z family of BTZ black holes, where the cycles are labeled by some tau, which is appropriately transformed under some element of SL2Z from that of the original torus characterizing empty AdS. This is the full set of smooth solutions of Einstein gravity. Maloney and Witten said the sum over smooth saddles, dressed by graviton excitations around them, is just a sum of SL2Z elements. I'm going to put a prime here. This isn't exactly correct, but for the sake of this this moment, it is of Z AdS, where I just transform the modular parameter of my torus. And Z AdS3 is the classical action with the one loop excitations of gravitons around that classical action, around that classical set. Note that in CFT language, this saddle point partition function is just the vacuum character, because the saddle, right, empty AdS is just dual to the vacuum state, and the boundary graviton excitations on the spacetime are just Virasoro stress tensor excitations of the vacuum state itself. So Z AdS3 is just the back of gamma tau. So Maloney-Witten's proposal was to compute this modular invariant. It has all the saddle points we want. It has the graviton excitations around that. And it has nothing else. Can this be a candidate partition function for a consistent theory? And the conclusion they came to was no. And why did they come to that conclusion? Well, to make a long story short, so is this okay? Is this consistent? Their answer was no, because it turns out it's non-unitary. And at the time, they were worried about the fact that the density of states is actually continuous. We understand this better now as some sort of coarse graining of a large central charge spectrum. This, though, is a problem. We want a unitary CFT. That's what it would mean to be consistent and a reasonable definition. And they looked and found some negativities in the partition function, in the density of states, rather, that you get by transforming the partition function. And in later years, works by Benjamin, Oguri, Xiao, and Wang showed that actually the non-unitarity they found, well, it wasn't so bad, but there's an even worse one. There's a lot of negativity in the spectrum in sort of some regions which they hadn't considered before, of large spin operators. And so something needs to be done to augment this to make it consistent. Now, what that is a subject of ongoing research. And you might ask, does this mean that pure 3D gravity does not exist? And the answer is no, but what it means to be a theory of pure 3D gravity is something that you should think about harder and try to understand more deeply. Maybe you need to add some stuff which is not so obvious, which is not just smooth saddle points. I mean, clearly you do, but the question is, what is that? And what could you add that doesn't just spoil the pureness of the theory, bring the gap down a lot? There have been some proposals. Yeah.
Sorry, even staying with smooth saddles, I mean, this Z gravity that you've written down, this is a one loop approximation to some path integral in 3 dimensions, etc., right?
Well, the one loop thing
Is it a one loop exact?
Exactness.
Like, yeah.
It's perturbatively one loop exact. Yes.
And non-perturbative corrections will not restore unitarity or something.
Yeah. So there are no non-perturbative corrections just in this sort of bottom-up setting, by which I mean, like, yes. So in higher dimensions, right, there are non-perturbative corrections from rapid grains and stuff. If you had a string compactification down to AdS3 and you tried to gap the spectrum as much as you could, there might be non-perturbative corrections to this that are exponentially small in C. This really, in my opinion, should be thought of as a all orders in 1 over C statement, this one loop exactness. It could be that there's some non-perturbative stuff, exponentially small in C, that would be part of a genuine compactification that has a gap in the spectrum that one wants, but that to all orders in the semi-classical expansion is invisible. But for the sake of getting the main point, think of this as one loop exact, because this is just the vacuum character for some suitably defined central charge, and that when viewed as a C expansion is one loop exact. I mean, yeah, I personally am a little bit dissatisfied with the way this is discussed, because yeah, right, the formula for the vacuum character is just what it is. But I think there are different ways of interpreting the elements of the sum. Like, you can associate certain effects to certain backgrounds. in a way that might make that sort of misleading statement. So there are various proposals for things to do. Let me just mention, I mean, the sort of, you can add conical defects. This can fix the negativity, but has its own issues, and maybe more to the point, it's not really a theory of pure gravity anymore. You can preserve a Planckian gap, but you've added some matter, albeit very heavy matter. So it's not quite answering the original question. You can consider adding things which are not matter or not solutions. This kind of proposal of involving some off-shell configurations is motivated from considerations in one dimension lower. And there's a paper by Maxfield and Toriachi which tries to suggest what the final answer might look like. They don't give a kind of description for what to add, what it means. And there's a lot of literature I'm not alluding to here, just to be clear. And finally, you might say, let's just stop trying to construct a microscopic partition function and somehow think of the pure 3D gravity theory as capturing some statistics of CFT data, or perhaps capturing the average over some ensemble of unitary microscopic CFTs at large central charge. These are interesting ideas. There's something to them. I encourage you to read the papers. I think in the reference list I didn't really add the papers. There's just a note at the end saying papers on ensemble averaging. But it's a growing field. I'm really not doing justice to that idea here. But I'll just say it doesn't take the place of trying to find a microscopic partition function for theory in the bulk, which has as large a spectrum as possible and looks like the theory of pure gravity as we originally conceived it. These two things might not be incompatible, but they're just slightly different points of view. And so going back to, say, Witten's original philosophy of trying to find a partition function which describes a bona fide microscopic CFT with asymptotically large central charge, that's still a valid pursuit. And there's some interesting things one can do, and I think there's going to be more said about that in the coming months, that's for sure. But at this point, we're getting toward the end of the lecture. So obviously, there's a ton more that can be said, but let me just, well, conclude asking any questions and encourage you to ask me questions after we're done if you have more. So that's it. Thank you.
I have a question again about the discreteness versus the continuous, whether the spectrum is discrete or continuous. So for the black hole, do you expect that it's continuous from this CFT or not?
If you're asymptotically large C, then there's a sense in which it is continuous, which is that in a chaotic system, as we expect theory of gravity to be, the average gap between the states in the spectrum is exponentially small in C. So if you go to large C, this exponential spacing gets washed away, and you might have an effective continuous spectrum emerge, even if you're describing a sequence of chaotic theories at larger and larger C, which any large but finite C would have a discrete spectrum. That's one sense in which you might be okay with a continuous spectrum at large C, and I think that's really how we should think about it. There's also this kind of ensemble picture where if you imagine yourself at some very large central charge, and you imagine some space of theories which have spectra which all start around C over 12 and then differ in the details above that, but are actually discrete, then in some sense, averaging over their partition functions could give you continuous density. These two perspectives might actually overlap, but I think that's what I would say.
No, you have a question?
Would you say that your second point of adding off-cell stuff there, work by Maxwell to Riazi, somehow dictating us in the CFT side, the modular bootstrap side, to implement really this SL2Z modular bootstrap and not just the S? Because essentially what Maxwell described is that we need to consider this dimensional reduction of the handle bodies where it's an SL2Z cycle that is contractible, not just the thermal ADS and PPA. So should we take this as a message to go to the modular bootstrap side and search for this SL2Z to implement the more general SL2Z kind of bootstrap? Or
yeah, maybe so. I guess you could say that their effect is sensitive to all transformations of this type, where some kind of sum over images, where if you sum over S, 2 to the 2n S transformations, where n you sum over all the n's, gives the effect that they're talking about. So that's, yeah, in that sense, I think you're right. Yeah. They of course don't, though, write down a modular invariant ansatz that has the shift of the threshold that they predict from the JT point of view. So in that sense, they're not using SL2Z invariance fully. It's an open problem to write down even just a function with the spectrum, with the edge that they predict, and which is SL2Z invariant. This would be an accomplishment. So I guess my answer is yes and no.
Yeah, so in the usual bootstrap, you can, the CFT bootstrap with the crossing, you can read off this extremal spectrum, right? And extremal in the sense of bootstrap. So in the modular case, was there something interesting about this extremal spectrum? For example, the C over 6 seems pretty nice as a number, so maybe that's some nice theory.
Well, the fact that this is the large C asymptotic, yeah, I think actually a lot of these papers did not do that. In one of the more recent papers by Kami, Jetty, Hartman, and Tavdini, and also Hartman, Mazat, Rastelli, they do talk about the extremal spectra, but at finite values of C. I think the expectation is that, right, in a large C limit, the extremal spectrum would have continuous support above the threshold. So I'm not sure that's been looked at so closely, except at finite C, where there's been some interesting results there. Yeah, so in some cases, they've been able to write down the, a modular invariant partition function which has the gap they're talking about, and therefore they can treat off whatever they want, but they construct the optimal solution. Yeah, but somehow the belief is that the optimal solution doesn't exist for the bounds that have been derived so far. So
yeah, I think related to what you're saying, an extremal functional will inherently not have a continuous spectrum. It will just have only possibility for a number of zeros that's zero by order, but basically it means that the extremal functional will never show the behavior that you're expecting, and therefore it's also, I guess, to be expected that you will never get the optimal bound, because you're just not looking in a space of functions.
Can't the extremal functional depend on C in a way that the zeros coalesce?
No, I think that, okay, maybe you have to think in order of limits things if you're thinking of like the functional space being going to an infinite dimensional functional space, but any finite dimensional functional space will be a pretty bad approximation because you will just be putting like a handful of operators on what you want to be a continuum, right?
If you were to do a large C. Yeah, and then in finite C, you would not want or expect it to be a continuum.
Right.
But indeed, these types of questions are most sharply phrased in the asymptotic large C limit, where just doing what you're describing gets harder and harder. So I don't think it's incompatible. It's a matter of practicality. Right? I think I agree with everything you said, but just to be clear, the continuousness that emerges at infinite central charge is really in the limit. So you can imagine some extremal spectrum which has zeros which are collapsing down to some line. I mean, yeah, suppose you could show that you somehow look numerically at larger and larger values of C, and you can read off some scaling of the spacing. If you show that you model it and you say, oh, it looks exponential, like that would actually be very cool.